North American XB-70A Valkyrie, a flight interrupted. From the dawn of aviation, aircraft were seen as one of the most promising instruments of war. First, they served as merely eyes in the sky, reconnaissance platforms guiding armies below. Soon after, they evolved into devastating machines of destruction, capable of striking deep into enemy territory. Among the bombers conceived in the 20th century, one stands apart as both extravagant and elegant, a symbol of ambition and tragedy. This was the North American XB-70A Valkyrie, a bomber so advanced and futuristic that it seemed less like a weapon of war and more like a machine born of myth. The name itself carried weight. In Norse mythology, Valkyries were ethereal warrior maidens who soared over battlefields, choosing the slain and carrying them to Valhalla, where Odin gathered his army of the dead to fight against the forces of darkness. Yet while the mythological Valkyries promised a second life, albeit an afterlife, the Valkyrie bomber carried the opposite fate. On its wings, it bore not salvation, but certain death, swift, final, and absolute. The story of the Valkyrie began in late 1954, when General Curtis LeMay, the architect of America's Strategic Air Command, declared the need for a new bomber that could one day succeed the legendary B-52 Stratofortress. At that time, military planners doubted the future of subsonic bombers. The doctrine of the era held that only a supersonic strategic bomber, fast enough to outrun and outclimb Soviet interceptors and missile defenses, could hope to penetrate the massive shield of the USSR's air defense network. On November 11, 1955, the U.S. Air Force commissioned both Boeing and North American Aviation to refine their initial bomber concepts. The challenge was immense: to design an aircraft that could fly at sustained supersonic speeds. These two requirements, speed and endurance, stood at the heart of the Air Force's strategic vision, and satisfying them simultaneously was a nearly impossible task for aircraft designers of the 1950s. Boeing's entry, the Model 804-4, failed to meet expectations and was quietly set aside. A fascinating project in its own right, and perhaps a story for another time. North American, however, presented a design that captured the imagination of Air Force generals. Sleek, futuristic, and promising unprecedented performance, their proposal was chosen for further development. Thus, the project officially took on the name that would etch it into aviation history: the B-70 Valkyrie. The Valkyrie was conceived as a marvel of aeronautical engineering. It employed a canard layout, a smaller forward wing ahead of the main wing, for enhanced stability and control at high speeds. Its immense delta wing, sweeping back with graceful precision, gave it both strength and aerodynamic efficiency, while the twin vertical tails reinforced stability at Mach 3 flight. The fuselage, constructed with a semi-monocoque design, housed a cavernous bomb bay stretching 30 feet in length. This bay could accommodate a wide arsenal, both nuclear and conventional bombs, ensuring versatility in its destructive potential. Early in the program, designers also envisioned the Valkyrie carrying AGM-48 Skybolt ballistic missiles internally, while mounting cruise missiles under its wing. This mixed payload concept later found practical application on the B-52 Stratofortress. The Valkyrie was 185 feet long and had a wingspan of 105 feet. Due to its gigantic size, the wing area has reached 6,297 square feet. The cockpit for the crew of two was pressurized. The pressure inside was maintained at atmospheric pressure. That is, the pilots could do without high-altitude spacesuits. To improve visibility during the landing approach, the upper fuselage nose panel in front of the windshield was lowered. The B-70 Valkyrie received 6 single-circuit turbojet engines YJ93 GE3, which were placed in a monocoque in the aft fuselage. The static thrust of each engine was approximately 19,900 pounds. With the afterburner, this figure increased to 28,000 pounds. The launch on the ground was carried out using an airfield installation, from which the rest of the engines were started. The commission was inspired by a completely new, original technical solution that gave the B-70 Valkyrie exceptional flight performance. Recall that the maximum speed of the North American XB-70A Valkyrie bomber still remains a record and is Mach 3.1. At the same time, the flight range exceeded 4,000 miles. This is incredible because speed and range are often mutually exclusive due to the trade-offs that engineers have to make when designing an aircraft. Typically, an airplane flies either fast and close or slow and far. The idea behind the XB-70A Valkyrie was to critically increase lift by compressing the airflow. This concept was already used by NASA engineers at the time, but exclusively in experimental flights. Another feature of the XB-70A Valkyrie was the deflectable wing tips, which also contributed to the stability of the aircraft at high speeds by improving aerodynamic performance. When the wing ends were deflected downward, the aerodynamic focus of the aircraft moved forward and merged with the dense airflow created by the air intake wedge. As a result, the lifting force increased. Thus, it turned out to endow the aircraft with acceptable stability in both flight modes, subsonic and supersonic. One plane, 2 characters. This is the essence of the revolutionary XB-70A Valkyrie. However, the record-breaking airspeed performance revealed another problem. At Mach 3, some areas of the surface were heated to 626 degrees Fahrenheit. Therefore, the designers had to use stainless steel high-strength tool steel and titanium alloys. These materials retain high durability at critical temperatures, but at the same time have a good thermal conductivity. This is because the engine inlet fuel temperature limit is 302 degrees Fahrenheit. With the kinetic heating of the walls of the fuel tanks in supersonic flight, the temperature rises above this limit, and the tanks are located right in temperature-loaded places. What to do? Then the designers of the XB-70A Valkyrie decided to use laminated panels instead of the usual sheet metal cladding. They were used to make the skin of most of the wing, the lower and upper surfaces of the fuselage. The rest of the structure is made of high-durability titanium alloys. The second plane made its maiden flight on July 17, 1965. On the 46th flight on June 8, 1966, it crashed in a collision with an F-104 fighter. When filming a commercial for General Electric, it was planned to capture the combat flight of 5 aircraft: Valkyries, Lockheed F-104N Starfighter, McConnell Douglas F-4B Phantom, Northrop F-5 Freedom Fighter, and T-38 Talon. All of these aircraft used GE technology. Filming was almost over when the F-104 touched the right end of the XB-70 wing with its left wing tank. After the first contact, the F-104 rolled over and glided over the Valkyrie's tail, cutting off part of its right keel and almost completely removing the left keel. Starfighter's tank was depressurized and the fuel instantly ignited, exploded. The pilot died. The tests of the remaining first aircraft continued for another 2.5 years, but an accidental tragedy became the reason for the persecution of the project in the press. The creators of the XB-70 bomber and the generals from the U.S. Air Force were reminded of everything, both the prohibitive cost of the project. They decided to close the project. The first XB-70A Valkyrie made its last test flight on December 17, 1968, and on February 4, 1969, the Valkyrie was sent to the Air Force Museum. Beyond unfavorable press coverage, the North American XB-70A Valkyrie also drew heavy criticism within professional and military circles. The very premise of the aircraft, speed as its ultimate defense, was being undermined by rapid advances in guided missile technology. Unlike interceptor aircraft, surface-to-air missiles did not care whether their target was flying at subsonic or supersonic speeds. What mattered was detection and tracking. Once that was achieved, even a Mach 3 bomber like the Valkyrie was no safer than a slower counterpart. Today, they remain an essential component of the nuclear triad, alongside land-based intercontinental ballistic missiles and submarine-launched ballistic missiles. Their mission is not to outrun defenses. With the advent of long-range cruise missiles, strategic bombers no longer need blistering speed. What they require is endurance, flexibility, and survivability. For more localized conflicts, the task falls to tactical bombers. These aircraft emphasize high speed, shorter range, and increasingly stealth technology. Unlike the Valkyrie's brute force approach of using speed to evade threats, modern tactical bombers and strike aircraft operate effectively by minimizing their visibility, slipping past defenses rather than attempting to outrun them.